All right, welcome everyone. Happy Wednesday. Today we are moving into chapter 16. This is the final small trek of stuff that will be covered and is fair game for our exam next week. And so remember the quiz tomorrow that we have, quiz 4, covers 14.6. That was the stuff about directional derivatives and gradients. So how can you maximize or minimize directional derivatives? How can you calculate out a directional derivative itself, right? If you're given a direction. And then we also had stuff about upgraded versions of like tangent planes and all that sort of stuff. So we can calculate out tangent planes. That was 14.6. 14.7 was mins and maxes. We had 2 days for that. We had local mins and maxes, and that we had the determinant of the Hessian matrix and all that sort of stuff. And then we also had a day about absolute mins and maxes, right? And so we had to test the boundaries and all that sort of stuff. And then the stuff in Monday's class was about the Lagrange multipliers. This is mins and maxes when you have a constraint equation, right? So some additional equation about some min and max. So instead of being on some region, perhaps, you know, like a closed triangle or something like that, right? Usually in the Lagrange mins and maxes, you're on a specific curve, right? There's some constraint equation. So those are the three main topics for our quiz tomorrow. I think that's all of my admin stuff. Any questions before we jump into the math for today? Okay. Well then, why don't we go ahead and to bring this up. So in our pre-class video about 16.1, we start talking about vector fields. So instead of just an isolated vector here and there like we had in chapter 12, we now have vectors kind of at every single point in space or in a plane. So we slowly graphed a particular vector field in the pre-class notes. So this was f of x, y, and the vectors were given by negative y comma x. So you take whatever the x coordinate of your point is, right? And you put that in the second coordinate there, right? And you take whatever the y coordinate of your point is, and you put that in your first coordinate, but you make it negative, right? And so we got lots of little vectors here, and we plotted them, and this is kind of some sort of spiral field here. Then we talked about kind of one way that I think about vector fields is kind of these missing pieces. We've talked a lot about kind of when we have, you know, kind of one dimension into one dimension. This is a lot of our algebra stuff that we classically have done up until our course here. And then if you have two dimensions into one dimension, this is the case where, again, you have two inputs, x's and y's, and only a single output, like z's. So these ones kind of become our classic surfaces. We talked about like temperature functions. Those have maybe three inputs, x's, y's, and z's, and give you an output. And I usually visualize this as, you know, again, at every single x, y, z in space, there's some number floating there, right? That corresponds to what is that function's value or what is the temperature at that point, right? We've done a little bit of the one dimensions into two dimensions or one dimensions into three dimensions. Those are going to be planar curves and space curves. And the stuff that's missing is the vector fields. So now we're kind of dealing with two dimensions into two dimensions and largely three dimensions into three dimensions. Those would be the vector fields and kind of are filling in those last remaining bits in the table, I suppose. So that is the premise of the pre-class videos and everything. Were there any questions as you watch these? Any points of confusion that maybe I could help with before we jump into the new stuff? Okay, well then, I'll go ahead and switch over here. All right, so on to the new stuff. As this bit here mentions, vector fields do come up a fair amount. So here are velocity fields, for instance, over some maybe airplane wing or velocity fields of some river or something flowing. So again, kind of each speck of water has maybe a direction and a magnitude, right? Kind of how it's headed, if you think about some river. Likewise here, we have maybe a gravitational field, right? At every single point in space, maybe the Earth is pulling on objects. And so they're all kind of headed towards the center of the Earth there. And kind of as you get farther away, right, there's less of a pull, so less of a magnitude on these vectors. So all this is to say that kind of vector fields are reasonable. They do show up in nature and whatnot, and so they're worthwhile to study. A lot of these kind of in our class are going to boil down to things like force fields. So a field that's specifying some amount of force, like gravitational fields or like electromagnetism, things like this. So I'll go ahead and specify here gravity. Electromagnetism. And the other common one that we see are velocity fields. How is that water traveling, right? Because not only does it have a speed, but it also has a direction to it. So my claim is we've actually seen vector fields once before already, although we never really consider them, as full vector fields. We always kind of plug specific values into those. And so does anyone have a guess of what was the vector field that we've seen already? Got a guess? Okay, so slope fields from Calculus 1 would be kind of a good example of this. Yes, but I'm really kind of, I guess it's a vague question, but I meant for in our class here. At MSU, we don't actually do slope fields either. So you must have been like in an A, B, or BC calculus or something like this. I think they do slope fields, but yeah. It is, yes. So the gradient turns out is a perfectly fine vector field. So for instance, if I have some function, maybe x squared plus y squared, relatively simple one. If I calculate out the gradient, we're going to have 2x in my first coordinate and 2y in my second coordinate. Now, when we brought this up in 14.6, we always evaluated the gradient at a specific point, right? We were trying to minimize or maximize some directional derivative or evaluate out a directional derivative in a specific direction, right? And so we always plugged in a specific point into this. But if you just consider this and you say, well, what about the set of all points, x's and y's, maybe in a plane or something like this, then yes, this is a perfectly good vector field. And so with this, we get a few definitions, because this is kind of the nicest form of vector fields that we have so far. So we're going to call these things gradient fields. So a gradient field is a vector field that is found by taking the gradient of a function. So let me do maybe another example here. If I have the function x times y, then that means that the gradient of f, well, if I take a partial derivative with respect to x, I'm going to have 1y. And if I take a partial derivative with respect to y, I'm going to get x times 1. So here's would be an example of another gradient field. If we look kind of maybe from the view of rather starting with a function, if we start with the vector field, these get slightly different names. So a vector field F is called a conservative vector field. If it is the gradient of some scalar function. That is, if there exists a little f such that our vector field is equal to the gradient of little f. In this situation, f is then called the potential function. So my example here is, if we were to start with a vector field, and I'll make it very convenient on us, I'm going to start with a vector field of y comma x. My claim is that this is a conservative vector field because there exists a potential function. So I'll say since when little f is equal to xy, we have that the gradient of little f is equal to our vector field given. So a lot of what we're going to be doing in 16.3 is playing this game here, which is if I give you a vector field, is it conservative? And if it's conservative, can you find a potential function? So that's the game that we're going to be playing a lot in 16.3, the last section before our upcoming midterm exam. For now, though, we're going to be just calculating out gradient fields. I guess kind of on a quick side note here, when conservative, it's not like liberal conservative, that sort of thing, right? It's that it satisfies conservation of energy laws. So these turn out to be very important vector fields because they're conservative and they, again, satisfy some nice physical equations that we know and love. All right. Any questions before we move on? All right. Well then, I'd like to do kind of a classic style example here. I'm going to actually should probably remove this. This is kind of a mean way if you say none of the above, because the only really reasonable way to do these is by elimination. And so when I've seen these, if something like this was to show up on a quiz or an exam or whatnot, they usually don't give you none of the above. Because, right, we don't have time to plot this entire thing, but we can say which of these four here this needs to be. So the technique that we're going to use to try to identify which vector field this could be is that we're going to choose a specific point and see what the vector looks like at that point for each one of these vector fields. So let's go ahead and maybe start. So I'm going to go ahead and say, I'm going to choose the point when x is equal to 1 and y is equal to 1. So if I was to try my best to identify where that is, and it doesn't look like I have a vector exactly right there. So let's go ahead and maybe add one and guess kind of what it would look like. It looks like to me that all of these vectors really in the first quadrant here are pointing up and to the right. They're pointing more up than they are to the right, but all of them seem to be pointing up and to the right. So at 1, 1, there's some vector there, even though it's not being sketched actively, right? I had to add in my own little one here. But it should be something that's pointing up and to the right. So I'm going to go along in each one of these. So for instance, at vector field A, I have the vectors given by x, comma, x minus y. So that's going to be 1, comma, 1 minus 1. So this is the vector 1, 0. And if I was to sketch that vector, it is pointing to the right, but it's not pointing up at all, right? The x coordinate is 1, so it's positive. It's pointing in the positive x direction. But again, the y coordinate is 0, so it's not pointing up at all. So therefore, I know that A can't be it, and I can eliminate choice A, because again, all of the vectors around 1, 1 are pointing not only to the right, but they're also pointing up. We can play the same game now looking at B. So at B here, I have what? Y is 1, and x minus y, that's going to be 1 minus 1, is going to be 0 again. And so again, this vector here is going to be pointing just over to the right. And so I know that option B can't be it either. Option C and D both give 1, 2. Right? So when I plug in, everywhere I see an x, I plug in a 1. Everywhere I see a y, I plug in a 1. Right? We're going to get 1, comma 2 for both of these. So in both of these cases, they are pointing a little bit to the right, but more up. Right? Twice as much up as they are pointing to the right. And so, yeah, this kind of looks reasonable, right? So I wasn't able to get my full solution, but I was able to eliminate 2 of the 4 choices. So now I need to kind of try another point, and hopefully I'll be able to eliminate then one of these and not the other. So I'm going to go ahead and choose, let's see, looking at these here, I see that the second coordinate's exactly the same. The first coordinate is different. So I need to kind of tease out this first coordinate. One's going to be x and one's going to be y. So what I'm going to do, I'm going to choose the point x equals 1 and y equals -1. What this is going to do for me, right, is that C is going to be pointing to the right and D is going to be pointing to the left. I guess I can figure out the second coordinates as well. But so x plus y, 1 plus -1 is going to be 0 in both of these cases. So for C, this points to the right. Again, the vector 1, 0, 1 in the x direction, 0 in the y direction. And the vector D is going to point in the left direction, right? Because again, I needed to plug in y into my x coordinate, which was -1. So I have -1 comma 0. So it points to the left, and again, not at all up and down. So now I go over here, and again, I look at -1, 1 up here. And yeah, all of these seem to be pointing to the left, right? So it's not the best picture ever, but all of them seem to be pointing to the left. And therefore, right, I'm going to go ahead and eliminate C. So therefore, the correct answer is going to be D. Oh, I did a bad job here, huh? Yeah, thank you. Let's try this again. So yeah, I guess I was looking over here where x was -1 and y was +1. Don't make that mistake. So x is +1, y is -1. These seem to be pointing off to the right. Apologize for that mistake. All right. Any questions about this? All right. Well then, why don't we go ahead and continue? Another relatively nice question that you'll get, a fair number of these in the web work homeworks and whatnot, is just calculate out a gradient field. And so, I mean, the big thing is that you need to remember that the gradient field is just the gradient of f, and you don't need to plug in any specific x's or y's, right? Because we're going to consider this as a vector field rather than just a specific vector at a specific point. So for my first coordinate here, I need to calculate out the partial derivative with respect to x. Then in my second coordinate, I'm going to calculate out the partial derivative with respect to y, and that'll be my final answer. So when I go and I calculate out the partial derivative with respect to x for my function up here, I'm going to have 2y plus 3 minus, and the derivative of e is itself, multiplied by the derivative of the inside. So inside of e, we have -xy. And so when I take the derivative of this with respect to x, right, I'm going to get -1y, I suppose. I'll simplify that in just a second. Okay, now when I take the partial derivative with respect to y, I'm going to have 2x plus 0 if you'd like. You don't have to write this bit down. The derivative of e is itself, leave the inside alone. Then multiply by the derivative of the inside, again, with respect to y now. So I'm going to have, what, -x, and the derivative of y is 1 here. So my final answer, as clean as I can make it, is 2y plus 3 plus y e to the -xy, comma 2x plus x e to the -xy. Problems today seem a little bit easier than Monday, huh? It sometimes happens at the beginning of chapters, right? Kind of the chapter kind of builds on itself until the very end when, they get kind of extreme. But today, they're pretty nice, all things considered. Any questions? All right. Well then, I'd like to point out we brought this up a little bit in 14.6, and it's true for the full gradient fields as well. And so I'd like to kind of showcase a special property that we have here, and that's relating together level curves along with gradient fields. So I'm going to go ahead and draw some level curves, and then I'm going to compute out the gradient vector field, right? And I'm going to do all this, sketch it at 1 or 2 points on each level curve. So I have a specific set of level curves I'm interested in sketching, and then I'm going to do a couple gradient vector fields on each one of these. So let's go ahead and first sketch out our level curves. So if k is equal to 1, remember these level curves, these are all the outputs for our function. So it'd be that the function is equal to 1, x squared plus 4 plus y squared over 9. So again, I'm dealing right now with k equals 1. Then we'll do k equals 2 and then k equals 4, right? So it's given us our specific set of level curves here. Now, just by looking at this, I know it's going to be an ellipse, right? Because I see the x squared plus y squared. And that division by 4 and that division by 9 is just kind of squishing it a little bit in the x direction and in the y direction, right? And so, but since my picture and everything, it does have these axes, let's try to get a little bit better of a picture than just drawing some random ellipse. So in order to get a bit of a better picture, I typically like to draw the vertices. And so, for instance, I'm going to first set when x is equal to 0. When x is equal to 0, this is going to give me that 1 is equal to 0 plus y squared over 9. So that's going to give me 9 is equal to y squared. So y is going to be plus or minus 3. So I know 2 points here are when x is 0, y is going to be plus or minus 3. Now, if I wanted to do the other vertices, this is going to be when y is equal to 0. Then I'm going to have what? X squared over 4 equals 1. Plus 0 if you'd like, because now y is 0. So therefore, 4 is going to be equal to x squared, or x is going to be equal to plus or minus 2. So when y equals 0, I'm going to have x is plus and minus 2. So my ellipse in this case is going to look something like this. All right, well, we have one level curve down, 2 more to go. So I'm going to go maybe a little bit faster now. So when I do the level curve of 2, that means we're going to have our outputs here are 2. Again, if I want to get a little bit more of a detailed picture, I'm going to graph my vertices for the ellipse. So when x is equal to 0, I'm going to have 2 is equal to y squared over 9. That gives me y squared is 18, or y is going to be plus and minus root 18. Plus and minus root 18 is a little bit more than plus and minus root 14, sorry, root 16, which is 4. So root 16 is close by this. Of course, you have calculators and whatnot handy, so you can get kind of even more values, even more accuracy. But I know this is going to be plus and minus 4 and a little bit more. So y is going to be plus and minus 4, a little bit more than that. Not quite root 25, though. That would be 5, so somewhere closer to 4. Then if y is equal to 0, I'm going to have 2 is equal to x squared over 4. That's going to give me x is going to be plus and minus root 8, which is pretty close to root 9, aka 3. Just a little bit shy of it. Right? So I'm going to look about halfway point and go a little bit shy of that. And that's going to be my good enough sketch for root 8. All right, one more to go. When k is equal to 4. So 4 is equal to x squared over 4 plus y squared over 9. Again, trying to get a little bit better of a picture here. So when x is equal to 0, we're going to have y squared is equal to 36, or that's going to give us y is plus or minus 6. When y is equal to 0, we're going to have x squared is equal to 16, so x is going to be plus or minus 4. All right, so not bad review here, especially the midterm will cover level curves as well, 14.1. But now my claim is that these are somehow specially related with our gradient vector field. So let's go ahead and spend a little bit of time now calculating out our gradient of f. So I look at my function, x squared over 4 plus y squared over 9. First, I take an x partial derivative. So I'm going to have 2x divided by 4 plus 0, I suppose. And then I take a y partial derivative. So I'm going to have 2y divided by 9. Bless you. And I'd like to ideally graph a few points on each one of these level curves here. So maybe let's go ahead and first plug in, well, an easy one would be like 2, 0 or something like this. So I want the gradient of f at 2, 0. So when I do that, let's see, I'm going to get x is 2. So 2 times 2 is 4 divided by 4. And y is 0. So 0 divided by 9 is still 0. So I'm going to have 1, 0. So at the point 2, 0 over here, my vector is pointing off to the right and not at all up and down. So we have a vector that looks maybe like this. Should go again, kind of distance 1, right? 1, 0. That's my vector. Okay, we could also do something like 0, 3. So what does the gradient look like at 0, 3? So 0, 3, if I draw this on my level curves, would be up here at the top. And 0, 3, if I plug that into my gradient field, I'm going to have what? 0, comma, 2/3. So this is pointing not at all left and right, right? But it's pointing up by 2/3. So maybe I'll won't sketch every single one of these, but can anyone remind me the gradient versus level curves? What special property are they supposed to have? Yeah? Close. I think you mean the right thing. Perpendicular, right? So they're perpendicular to the level curves, or perpendicular to the tangent lines, right, of these level curves. So yeah, if we were to continue this and draw more of our gradient field, right, everywhere at every point here, we would find that our gradient field is going to be perpendicular to these level curves. So no matter what point that you choose, you're going to have a bunch of perpendiculars to our level curves. And same thing down here. So there's a few of our gradients on our level curves. So this just means that if you can visualize either the level curves or the gradient field, you know what the other one kind of has to look like. In this case, all of the gradients are going to be coming out, right, pointing in the outward direction here, kind of radially away from the origin. All right. Any questions on this one here? Well, I'd like to give you guys an opportunity to try one then. Same sort of deal, different function. So please take 90 seconds, 2 minutes, see how far you can get with this one. You can draw at least one of the level curves and then draw maybe a few gradient vectors on it. quick hint here, just in case if anyone's stuck. Before, when I plugged in my K value, I could look at it and say, ah, they're ellipses, right? But when I plug in my K value here, I have no idea what this thing is, right? So in general, when we'd like to sketch curves, it's best if we have a y equals. So if you can somehow make this a y equals, by and large, that helps us identify the curves, typically as fast as possible. There's a few exceptions like circles or ellipses and things like this, hyperbolas, but in general, if you can get a y equals, we're kind of golden. So that's what I would suggest. All right, let's try to finish this one up together here. So when I plotted these three-level curves, you can see solving it y equals made it much easier to sketch these. So y equals x is kind of the classic line, slope 1, intercept 0. Y equals 3x, a little bit of a steeper line, right? Slopes 3 there, still intercept 0. And y equals negative 2x. This is still going to be through the origin, but now it has a negative slope. So here are my three level curves, close to my level curves here. And so that we know that our gradient field is going to be perpendicular to these. So I already know based on this that we're going to have some sort of like almost like spiral field. And maybe they're pointing off to the right like this, or maybe they're going to be pointing off to the left like this. I really don't know, but I know that it's going to be either circulating kind of around the origin, either in the clockwise or counterclockwise direction. So that's kind of what I'm expecting based on this picture here. So in order to figure out which it is, right, I need to calculate out my derivatives. So let's go ahead and do that. Calculating out our gradient of f. First, we take a partial derivative with respect to x. Now, with this right here, we could use the product rule. We could use the quotient rule. We could actually, because there's no x's in the top whatsoever, we could just use the power rule. I'll go ahead and do that method here. So I'm going to realize that this is equal to y times x plus y to the negative first power. And so when I take the derivative of that with respect to x, the y is along for the ride. When I take the derivative, the negative 1 is going to come down. I'm going to reduce my power by 1, leave the inside alone, then multiply by the derivative of the inside, again, with respect to x. So it's just going to be 1. If I take the derivative with respect to y, though, I don't have this luxury because we have y's in the top and the bottom, right? So it's neither a constant, and so we really have to use the quotient rule. We could use the product rule if you'd like, again, by rewriting it like this, but I'll use the quotient rule here. So I have the derivative of the top times the bottom minus the top times the derivative of the bottom with respect to y, all divided by my bottom squared. Let's take one line to rewrite this. Again, unless I'm actively doing calculus, I really don't like the negative exponents. I find them more confusing than they're worth. And so I'm going to go ahead and write this as negative y divided by x plus y quantity squared. I can really feel that there's division and all that sort of stuff. And for my second one, let's see, I'm going to have y minus y here. And so I'm going to have x divided by x plus y quantity squared. So now let's go ahead and plug in a few things here. So for instance, on my first level curve, if I plugged in 1, 1, that would be a fine point to plug in. On my second curve, I could do, for instance, 1, 3. And on my third curve, maybe I could choose 1, negative 2. So there's at least a point on each one of our curves. Again, 1, 1 is going to be this point here. Oh, sorry, did I do? Yeah, 1, 3, good. It's going to be up here. And then 1, negative 2 is ideally down there. All right, so when I plugged in 1, 1, I'll have negative 1 divided by 2 squared. It's going to be 4. And then 1 divided by 2 squared, that's going to be 4. So if you'd like to, you can factor out the 1/4. And you really see that the direction is negative 1, 1, and it's just being scaled down a little bit. So at this point, 1, 1, we're headed to the left and up, and it's been scaled down, right? It's not, it's only, by a factor of 1/4. A relatively short vector here. Let's try that again with 1, 3. So if I plugged in 1 everywhere I see an x and 3 everywhere I see a y, I'm going to have negative 3 on top. 1 plus 3 is 4. Square that, I get 16. And then I'm going to have 1 divided by, and again, 4 squared is going to be 16. So this is going to be a scaled down version of negative 3, 1. So negative 3 is off to the left quite a bit. 1 is going up. And it's going to be scaled down by 1/16. So maybe even shorter than that. But now we see that from these, we seem to have like a, clockwise rotation. Last one here. So when I plug in 1 everywhere I see an x and negative 2 everywhere I see a y, we're going to have what? 2 here. And this is going to be what? 1 plus negative 2 would be negative 1. Square that, we get 1. And then here we're going to have 1 divided by 1 squared. So this is going to be the vector 2, 1. So to the right and up, not scaled down at all. To the right and up, something like this. So again, some sort of rotation field here that we can visualize thanks to knowing what the level curves look like. Any questions about this one here? I noticed the last one, it didn't have this extra bit here. It says that x cannot equal negative y. What was all that about? Yeah? Yeah, exactly. So that's the denominator. If x was equal to negative y, you'd be dividing by 0, right? And you're not going to get a picture there. So that's why you need that extra kind of exclusion, just to say that there's not going to be any picture along that line there. Good. Last chance. Any questions on this page? Oh, sorry. Yes. So I guess when y is equal to negative x, that would be like, oops, I didn't mean to have my highlighter. we'd have something like this. So that was y is equal to negative 2x there. Y is equal to negative x is something like this. So I mean, we could put like a dash line to say, right, there's not going to be any pictures here whatsoever. And actually, this shows you why I didn't choose the origin at all, right? The origin is kind of a very special place. It's in this case, it's going to be highly undefined here. And you can see that it's always going to happen when you have multiple level curves crossing, right? Because it wants to take on kind of every single value. And so this is not a bad one if you have some time after class to sketch this function and see how monstrous the origin looks. You basically get like a straight line up and down. It's quite an interesting sight. Maybe if we have some time before class next time, I'll come prepared with this one kind of graphed or whatnot. Did that answer your question at all, or did I make any sense? Okay, great. All right, well then, the last page is kind of a prelude to next time, so 16.2. And just kind of an FYI, we've focused a lot on 16.1 in today's class, and I think it's important to kind of build a solid foundation on this sort of stuff. In the web work homework, basically you're set for problems 1 through 6. All of the stuff that we've learned here today and in the pre-class video, you're golden on. For web work problems 7 and 8, the last two web work problems, they rely on you being able to do a line integral with a scalar function. This is the stuff that we do in the 16.2 pre-class video. So I would recommend that you watch that pre-class video before attempting problems 7 and 8. Or of course, Friday's class, right? We will have Friday's class before this stuff's due and whatnot. So you could also just kind of hold off and wait until Friday's class, and we'll learn this stuff in great detail then. But make sure to watch the pre-class video before trying problems 7 and 8. Otherwise, you'll be a little bit sad. So the bit that I want to talk about though here is giving kind of some intuition on what we'll have are line integrals over some vector fields. So this is kind of the end of 16.2 is what we're hoping to get to next time. And so I have some pictures here, various vector fields. I haven't told you what the equations are or anything like this, because we're just trying to get some intuition. But ultimately the question is the vector field helping or hurting in pushing particles along the curve? So in this case, I have P to Q, and quite often when I'm imagining these things, I'm imagining that like the child's toy with the like the beads on there and like the or like a roller coaster sort of deal where it just kind of has these metal paths, and then you can move the beads kind of along it back and forth. Do you guys kind of know what I'm talking about? So the particles here, the key thing is the particles are not going to be removed from the metal rod, right? So no matter how much your vector field is pushing or pulling or anything like this, particles are traveling from P to Q. And the question again is, I mean, basically, if we had one of these toys and we had a bunch of these fans going sort of deal, would that vector field, would all this wind kind of help push those beads along the curve, or would it hurt? And so when I look at something like this, I see that as we go from P to Q, there's a lot of these vectors that would like the particles to just go off the curve, right? They're pushing off to the right. But again, we're not gonna blow any of the particles off the curve here, but they are kind of, there is some component of these vectors that's pointing upwards. So right, there is some helping going on here. We are kind of helping those particles move off of P and towards Q. But then later on, kind of as we get up here, it looks like now all of our good deeds that have been done seem to be canceled out by the second half of this, right? So these ones seem to be pushing against particles moving from P to Q. So overall, when I look at something like this, I say that the vector field, it has some time when it's helping and some time when it's hurting. And it seems like these cancel out with one another, that it neither helps nor hurts. And it turns out what we've shown, or what intuition I'm trying to help with here, is that if you were to calculate up this line integral here, that you would get 0. When the vector field neither helps nor hurts, the line integral will equal 0. Basically, we're adding up the influence of our vector field as we go along the curve. So this is an integral over our curve, C. and we're adding up, right? Anytime you have an integral, you're adding something up. And this is adding up, how is the vector field influencing particles traveling along this curve? Now, by comparison, if we look at this second vector field, as I go from P to Q, I can see that in this first half here, the vector field is hurting me, right? It's not liking particles going from P to Q, right? It would rather them stay at P. And likewise, in the second half, there's some downward component of all of these vector fields. They would rather the particles stay at P here. And so in this case, if you were to calculate up and add up the influence of your vector field as it acts upon particles on your curve, you would find that you would get a negative answer. That again, it's kind of hurting more than it's helping. So again, F is making it harder for particles to move from P to Q along this curve. And so it turns out when we calculate out this line integral, the answer ought to be negative. And then finally here in this picture, we have that we're helping particles, right? Kind of at the beginning here, again, the vector field's really not helping or hurting. It's perpendicular to the movement of the particles. So here it's near P, it's really not doing much of anything. But then eventually it kind of turns and it starts to kind of help the particles move towards Q. And so overall, this is going to be helping more than it's hurting. And so if we were to add up the influence of our vector field as we travel along this curve, we would find out that you should get a positive result. So these things that we end up calculating next time, this is kind of the intuition. This is at least able to visualize when it should be positive, when it should be negative, or when it should be zero. So that's going to be where we stop here. Again, to do the last couple problems in the web work homework 7 and 8, please make sure that you view the 16.2 pre-class video before you attempt those ones. Okay. All right. Well, best of luck on your quiz tomorrow, and I will see you guys on Friday, and we'll do more of this stuff, line integrals.